So in this video, we want to begin classifying differential equations in various ways. We've already talked about one way of classifying differential equations. We've divided them up into what are called ordinary differential equations, ODEs, and PDEs, partial differential equations. But today we want to talk about another way of classifying by order and linearity, and that's going to be the topic of today's video. So we learned last time about some examples of differential equations that we're going to learn in the process of this class how to solve. So one, for example, is y prime equals ky. I believe we talked about this one. Maybe I wrote dy dx last time, but this is a totally equivalent formulation. This is sometimes referred to as the exponential growth equation. I don't think I named it last time, but that's what it's sometimes called. And the reason is because the solutions to this thing look like exponential functions, okay? This is the differential equation which governs the phenomenon of exponential growth, and that hence the name, okay? And this is an ordinary differential equation. It involves only ordinary derivatives, no partial derivatives involved. But we also can say about this equation, so I'll say this is an ordinary differential equation, it's an ODE. But we can also say about this equation is that it's a first order equation. This is the notion that I want to get at today in this video, or one of the notions. It's a first order equation because it only involves the first derivative of y. No second derivatives in sight in this problem, in this equation. We can contrast that with something like the formulation of Newton's second law that I talked about at some point. Force is equal to mass times acceleration, but rather than writing acceleration as just a, let's display it as a second derivative. It is d squared s dt squared, where s is displacement. So this is, of course, Newton's second law. Very important for physics. And this is, again, an ODE. No partial derivatives in sight. But now, rather than being a first order equation, it's a second order equation. Then also we talked last time about the heat equation, another equation that we're going to learn how to solve. So this is the equation partial u partial t is equal to some constant k times the second derivative of u with respect to space. So imagine a one-dimensional bar, the heat at a particular position in the bar x at time t being given by u of xt. Then we can talk about the partial derivatives of u, and there is a equation which called the heat equation, which determines the distribution of heat through time. And of course, this now isn't an ODE any longer, it's a PDE, and we say it's a second order equation. Okay, it's second order despite having a first derivative in the mix, right? This mixes both the first derivatives and the second derivatives of the heat of u. But nonetheless, we take it to be a second order equation because the highest order derivative, which appears in the equation, is a second derivative. And so if we wanted to make a definition out of this, that would be very simple. We would say that the order of any differential equation, so I'm defining this, is the highest order derivative which appears. In the equation. Okay, so this should be a relatively common sense definition for what we mean by the order. And this is a way of classifying, of course, differential equations. We're also going to learn about what are called linear equations. So this is the notion of order. There's also a notion of linearity, and this is a little bit more complicated. So to understand this, linearity. And let's just stick to the world of ordinary differential equations for now, ODEs. And by the way, ODEs are going to be by far the thing that we concentrate on the most in this course. Okay, we will have occasion, I hope, to say something about the heat equation near the end of the semester, but that's not for a long while yet. Okay, but when it comes to linearity, an equation is linear if it can be written in a particular form. And I want to describe what that form is. So maybe I'll make a definition. A ODE is linear if it can be written in the form, and I'm going to write the form for you now. So we're going to have n plus 1 functions, which are going to be denoted by a. So we're going to have a sub n of x times the nth derivative of y. So dn y dx to the n. Now, let's be clear. This thing right here denotes the nth derivative of y with respect to x. Okay, so if we replaced n by 2 here, that would just refer to the second derivative, of course. But this is the nth derivative, okay? And I'll say more about this in just a second because I'm not done yet. This is just one term of the equation. We keep going. The next term of the equation is a sub n minus 1 of x times dn minus 1 y dx n, okay? And we keep going like this. So I'm going to denote the state of affairs with a dot, 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 like this. Then we're going to have what's called the order 1 term. So that's going to be a1 of x dy dx. And then we're going to have the order 0 term, which is a naught of x times y. That's the 0th derivative right there. I'll say all of this in just a second. And this is equal to some function b of x. Okay? This is the general form of a degree n linear now ordinary differential equation. A linear equation is one that has this particular form. So to be absolutely clear, this here refers to the nth derivative of y. This is the n minus first derivative of y. And we keep going all the way down. And of course, we regard y itself as being the 0th derivative in some way. Like we did no derivative, so it's like the 0th derivative of y. And all these other things, like this a sub n, this a sub n minus 1, this a sub 1, this a0, this b, these are all functions. Okay, they're not numbers, they are functions of x. Okay, so I'll write where a sub n minus 1, all the way down to a1, a naught, but also this thing b over here are functions. Okay, so this might be a very different notion of linearity than the one you're used to. You're used to linearity because it's got this word line in it. It's got this word line in it. You're used to it referring to something having to do with lines. But we in mathematics have, and in physics and in many different enterprises have generalized the notion of line to include other types of objects, things like planes and spaces with particular kinds of structures. And it turns out that ordinary differential equations which have this particular form are called linear. Okay, so this is the abstract definition. It's hard to look at. So let's do some very concrete examples of this, of both linear differential equations, but also nonlinear ones. So here's a great example. Y prime equals ky is linear. This is the exponential growth equation. Why? Because we can subtract ky from both sides. And get this equation. Totally equivalent. All I've done is subtract ky from both sides. This is totally equivalent, but now this, okay, has this form. Do you believe me? You should. Let's just make sure that we see it very concretely. If we compare this, okay, if we compare what we've got here with this general form here, we can identify a sub 1 of x is going to be just the number 1. That's the invisible 1 that nobody bothers to write in front of y prime here. Okay, so a sub 1 of x, looking up here, a sub 1 of x is just going to be 1 times y prime. A sub 0 is going to be, of x rather, is the constant function negative k. That's going to be right here, negative k. And then b sub x is 0. And if we were to make everything else 0, all the other coefficients be 0, maybe I'll write that. And a sub I of x is equal to 0 for all I greater than, or, well, greater than 1. Okay. So if we make these designations for the a's and for this b, then we can see that this equation satisfies this form. Okay, so it's a linear equation. Newton's second law is also a linear equation, and it's a second order linear differential equation. And you can check that in this case, that a sub 2 is going to be m, a sub 1 is going to be 0, a sub 0 is going to be negative f, depending on how you solve it, and b sub x will be 0, right? Or, I mean, frankly, you could also, write it in a different way. I could have done that here, where you make b sub x be f. I don't know. Maybe we don't need to go into this. But like, as long as we can write an equation in this form, then we can conclude it's linear. Let me give you just another example that's kind of simple. Suppose that we had something like x squared y double prime plus 3x plus e to the x times y prime minus 15 sine to the 3/2 power of x times y equals 9. Okay. I know it looks horrendous, but it is a linear differential equation. Okay. Sorry for the brief interruption there. This is a linear equation, though, is the point I'm trying to make, okay? And you can hopefully see this pretty straightforwardly. This is a sub 2, this is a sub 1, this is a sub 0, and this is b of x, okay? And you can see these things can get very complicated. These are very complicated coefficients, if you like, of the derivatives that we've got involved in this second order linear differential equation. Let me give you an example of a nonlinear equation. So let's say that we had an equation like y times y prime equals 5. Okay, this is nonlinear. And the reason is because in a single term, we have the y's being mixed with the y prime. Right, and that's a telltale signal that this is a nonlinear equation. Okay, if we had something like this, y squared minus y triple prime equals 7. This is nonlinear because you've got a power of y happening there. Okay, so this is again a nonlinear equation. All right. You can have x's mixed in there too, I suppose. If you had x times y prime plus 3y cubed, okay, equals 18, this is again a nonlinear equation. This example here is linear. This example here is linear. This is not, this one down, these three examples down here are all nonlinear examples, okay? In this class, we're gonna focus quite a lot on the linear case. The nonlinear case is very, very difficult, but I do wanna say that it's not like nonlinear equations don't occur in nature, they occur in nature all the time. And in fact, this is part of what makes science so difficult, is that sometimes things are described by nonlinear equations. So one really potent example is through the analysis of a pendulum. So if you've ever seen a pendulum swing back and forth, you can do a physical analysis using like free body diagrams and that sort of thing. And you'll come up with a equation of the following form: theta double prime plus sine of theta is equal to 0. So this is sometimes called the pendulum equation. And this is a very nonlinear equation, and that's because the theta is being stuck into a function. In this case, the dependent variable theta, and presumably the independent variable is time, is being stuck into a function. That makes this one a nonlinear differential equation. Even though it is a differential equation, it's a second order differential equation, but it is nonlinear, okay? Maybe just as a quick comment, I know this video is getting long, I realize. I don't know how that happens, but even though this is a nonlinear equation, what many physicists and engineers do when confronted with an equation like this is to linearize it, okay? And the way that they do that is they might think about, like, what does sine of theta look like when theta is very, very close to 0, for example? And this is where you can use the tangent line approximation to the function. This is where Calc 1 type stuff can come into play, and you can transform this into a different equation when theta is small. When theta is very, very close to 0, so I might say theta is approximately 0, you can write down the equation theta double prime plus theta equals 0. Because when it turns out when sine theta is very small, when theta is very small, sine theta is well approximated by just theta. And that's because the tangent line to the graph, y equals sine of x, is equal to x. We'll be less concerned about such issues in this class, but I thought it would be worthwhile just to say that out loud for you at least once, so that you understand that even though you might have a nonlinear equation in your life, sometimes you can linearize it. Okay, that's enough for this one.